Hello again. In this lecture, we will start a new chapter of mechanics and we will discuss about the analysis of structures. Now, so far, we have dealt with rigid bodies. Rigid bodies were idealizations in the sense that there's no such thing as a rigid body. Everything deforms under the action of the loads, but we made these assumptions in order to simplify the analysis. And for rigid bodies, we looked at the effect of the external forces in order to analyze the equilibrium of that rigid body. For structures now, which are rigid assemblies of elements, as you will see, we will study, in addition to the equilibrium of the overall structure, we will study the forces that are internal to the structure. We will calculate these forces that hold the structures together, and we will see how we can do that. And basically, we will use the action and reaction principle between the connected elements. So, what is a structure? What is the definition of a structure? Well, a structure is a system of connected members that are built to support or transfer forces that are applied to the structure, and then to safely withstand these forces and transfer them to the supports of this structure in question. As part of the analysis of structures, the first group of structures that we will deal with are called trusses. And I'm going to now draw a few examples of trusses, and you will see that you can probably already recognize some of these, as you've seen them somewhere, in the surrounding environment. So, for example, this could be one truss, simply supported on a pin and a roller. Horizontal members, vertical members, and some diagonal members. This specific configuration of a truss is called a Pratt truss. And you can see that all these members in the truss are straight members connected together. Another type of truss, slightly different, in the sense that the edge members are now sloped, and also the internal members, the inside members, are all sloped, so there are no vertical members anymore. So this is another type of truss, and it's known as a Warren truss. Or you may have something like this, in which the external shape is similar to the Warren truss, as you can see. And now we have vertical members, and we also have diagonal members. But now diagonal members have, as you can see, this letter, a horizontal V, or together with vertical members, they look like the letter K, so hence the truss is called a K-truss. And by now you probably have recognized this type of structures. You can see them in bridges, for example, road bridges, major road bridges, or railway bridges, or you can see them even in roofs. For house construction, you can see them made of wood before the actual roof is completed, or if you go shopping at the large brick stores, say Walmart, Future Shop, so forth, if you just look above, you can see that the roof is also supported on these kind of structures, trusses. What makes these structures particularly common is that if you look carefully, they're made of an assembly of triangles. So everything, the whole structure, is made of triangles that are joined together side by side until the whole configuration of the truss is defined. Now, why triangles? Why are these triangles, as you just saw, why do they constitute the basic element of a truss? Well, the reason for that is, if we look at a triangle, so let's say we have three straight members, like three bars, that are connected together by pins, so the members can rotate relative to each other at each connection, but all of them are connected in a triangular configuration, like the one that you can see now on the screen. Well, that constitutes a rigid structure. A triangular structure, a triangular figure is rigid, even if the members are pinned at the ends. They create a rigid figure. Now, if we built a similar structure but with four members, say like a rectangular or a parallelogram figure like this one, well, we can see very easily that this is a deformable figure. It cannot be rigid in this configuration, and this type of figure would not be suitable to be part of a truss, because it's not rigid, obviously. Can we make this figure rigid? Well, yes, but then we would have to add a diagonal bar to the four members, and hence we divide the original figure into two triangles that are side by side, and now each triangle is a rigid figure, so two triangles together then will define a rigid structure. And this is the principle behind the truss. So trusses, again, are made of an assembly of triangles. Each of these triangles is rigid, so therefore the whole assembly will also be a rigid figure, a rigid structure. Now, in order to simplify our calculations, we make a few assumptions, as we did in general for all structures. The first important assumption that we make is that all the members in a truss, which are straight members, are pinned to each other at their ends. So that means that even that in reality these members are rigidly connected, maybe through bolting or welding, so they normally would not be free to rotate relative to each other, because when these connections are built, it is ensured that the longitudinal axes of the straight members intersect all at the same point. Then that point of intersection will act, as you can imagine, as a particle. So all these members intersect at a point. They join into a particle. So that joint is like a particle. And as we remember from particles in two dimensions, there's no rotational effect of the particle, so there are no moments associated with the particles. So therefore, even if the connection is rigid, these joints can be assumed as being theoretically pinned. Now, the second assumption that we make is that all the external forces that act on the truss are applied at the pin connection only. So regardless on how and where the forces are in reality, there should be a system in place that will transfer these forces directly to the joints of the truss at the pins only. There are no forces applied on the members externally. Now, having satisfied these conditions, we need to introduce another concept. And this concept relates to two-force members. It's a very important concept that you need to understand and master from now on. Maybe not that fundamental for trusses, but very important in the future. Now let's see why is it important though for trusses. So if we have a member, a straight member like the one in a truss, which is pin-ended and has some forces applied to it, we will end up with reaction forces at the ends of the members of the truss in two directions: horizontal forces and vertical forces, because the ends are pins. However, if the pin-ended member, which for trusses these members are straight, but in general they may not be necessarily straight, and if these members have actually no forces applied along their lengths, so they can have forces applied at the joints, but nothing along their lengths. And when I say forces, that includes moments as well. So the member is clean of any applied forces. Then this member would be a two-force member. So a member satisfying these two conditions, pin-ended member with no forces or moments acting along the member, will be a two-force member. And a two-force member is characterized by the fact that the end reaction forces will be directed along the line connecting the member ends, the pins at the end of the member. In other words, for a straight member, this would be the member itself, the longitudinal line of the member. So the only reaction forces at the pin ends will be the ones in green, and the ones perpendicular to the member in this case will be zero. This is a very important concept to remember. For a two-force member, the forces at the ends of the member are directed along the line that connects the ends of the member. Now, because in a truss all members are pin-ended and all forces act at the joints only, all the members in a truss will be two-force members. That means that if we draw the free body diagram of a member in a truss, like this one, say the member is in tension, so the forces tend to make the member longer when they act on the member. So that would be a member in tension. Then these forces, as you can see, are directed along the straight member. In a similar fashion, if the member is in compression this time, so the forces are directed like so when they act on the member, making the member to become shorter due to the action of these forces, then the member is in compression. Now, the important thing is actually, from an analysis point of view, not how the forces act on the members, but how the forces act on the joints. So if I'm drawing now the joints at the ends of the member, separated from the member, drawing hence the free body diagrams of the joints and the free body diagrams of the members, then due to the principle of action and reaction, the forces on the joints will act in the opposite direction. So the blue and the red forces are the forces on the member, the green ones are forces on the joints. And we will use the forces acting on the joints in our analysis. Very important thing to remember. Now, in order to make a small analogy, because sometimes this is counterintuitive, Imagine that you have a pencil or a ruler that you hold between your palms, the palms of your hands, and if you push them together, you put the ruler or the pencil in compression. What is important in this case is what your palms will feel. The palms will feel that a ruler or pencil will push your hands in an outwards direction. So arrows pointing into the joint indicate compression. Arrows pushing into the joint indicate compression. Arrows pulling from the joint indicate tension. Very important to remember this concept. We use forces acting on the joints, and this is what we're going to represent from now on. So thank you very much for watching this lecture, and I will see you at the next one when we'll start analyzing trusses.